In the world of electronics, almost every circuit you can think of boils down to one fundamental choice: BJT or FET. They're basically the two heavyweights of the transistor world. And believe me, picking the wrong one can be the difference between a beautiful, high-fidelity amplifier and just a distorted mess. So, how do you choose? Well, let's break it down.
I like to think of it like this. Are you going to use a hammer or a nail gun? I mean, they both get a nail into wood, right? But you wouldn't use a nail gun for a tiny picture frame, and you wouldn't use a hammer to build a house frame. In electronics, BJTs and FETs are our tools. Both can switch, both can amplify signals, but knowing when to use each one, that's what separates a great design from a failed one.
So before we get into what makes them different, let's just quickly remember what they both do. At its very core, a transistor is just a controllable valve for electricity. You use a teeny tiny signal to control a much, much larger flow of power. It's this simple, elegant principle of control that powers pretty much every electronic device you own.
And they really have two main jobs. First, they act as these incredibly fast switches, creating the ones and zeros that are the bedrock of all digital logic. And second, they work as amplifiers, taking a tiny signal, say from a microphone, and boosting it into something powerful enough to actually drive a speaker.
All right, now for the main event. While they do the same jobs, the way they are controlled is totally, fundamentally different. And this single distinction, this one little detail, is the root of all their other characteristics, everything from their speed to how much power they eat up. So here it is, the big one. A BJT is current controlled. Think of it like a faucet you have to keep pushing on. You have to feed a small, continuous stream of current into its base terminal just to keep the main valve open. A FET, on the other hand, is voltage controlled. You just apply some electrical pressure, a voltage, to its date. Poof! It turns on and stays on. No continuous flow needed. This seems like a small difference, but it has absolutely massive implications. Okay, so let's put them head to head and see how this difference plays out when you look at a spec sheet. These are the kinds of things an engineer really obsesses over when they're designing something new. So take a look at that row for input impedance. Because a BJT is current controlled, it has low impedance. That means it's actively drawing current from whatever's trying to control it. But effect? It has an incredibly high impedance, which means it draws almost zero current. So why does this matter? Well, it makes FETs absolutely perfect for connecting to really sensitive sensors or weak signal sources without loading them down and messing with the very signal you're trying to measure.
And the performance trade-offs are just as clear. FETs are way, way faster switches, which is exactly why they totally dominate high-speed digital electronics. They also have amazing thermal stability. As they heat up, they naturally start to conduct less current, which keeps them from destroying themselves. BJTs can do the exact opposite. They can suffer from this really dangerous feedback loop called thermal runaway, where getting hotter makes them conduct more current, which makes them even hotter, and, well, you get the idea. Poof. Okay, so that's the theory, but where do you actually see these things in the real world? Let's look at two totally different applications: a nice hi-fi audio amp and, say, a modern computer processor. So let's say your goal is to build an amplifier that produces that rich, warm, powerful sound that audiophiles love. You need to boost a very small analog signal from a source into something that can physically move a speaker cone back and forth. For this job, you'd almost certainly reach for a BJT. And why is that? Well, BJTs typically offer higher gain, which just means they're better at multiplying a signal's strength. Plus, their specific analog characteristics are often what give that warm sound that people love. It's why they're still a staple in high-end audio gear. All right, now let's switch gears completely. Imagine your job is to design the core of a smartphone, a processor with billions, literally billions, of transistors that have to switch on and off billions of times per second, all while running on a little battery. Here, the choice isn't even a choice. It's a FET. Specifically, a type called a MOSFET. You'll find them in pretty much every modern processor. Their incredible switching speed is obviously essential, but maybe even more important, because they're voltage controlled and draw almost no current to stay on, their power consumption is ridiculously low. And that right there is the secret to making your phone's battery last all day. Before we wrap up, there's a really, really important practical difference between these two components that every hobbyist, every tinkerer, every engineer needs to know. It's all about how you handle them. So listen up, because this could save you a ton of time, money, and frustration. One of these components is way more delicate than the other.
MOSFETs are extremely sensitive to static electricity. That tiny little spark you get when you touch a doorknob, that can carry thousands of volts, more than enough to permanently destroy the incredibly delicate gate structure inside the component. BJTs, on the other hand, are generally much more rugged. So the takeaway is simple. If you're working with FETs, you always use an anti-static wrist strap. No excuses.
So in the end, it's really not about which transistor is better. It's about understanding the specific demands of your circuit. Are you trying to amplify a smooth analog signal, or are you switching digital ones and zeros at lightning speed? The answer to that question tells you exactly which tool you need for the job. And that kind of brings us to our final thought. Right now, FETs completely dominate the digital world because of their speed and efficiency. But research into new materials and new designs is happening all the time for both types. So the real question is, as our technology keeps evolving, which of these fundamental tools will be adapted or maybe even combined to build the next generation of electronics? It really makes you wonder.